Hi everybody, it's Dr. Chabot, and in this video we are going to learn how to analyze circuits that have multiple capacitor combinations. So here are clear steps for analyzing this type of circuit. So I'm going to work through an example also, but I want to first just highlight the key steps that you'll see will apply with all of them. First, we want to talk with the entire circuit first. So we're going to look at the entire circuit as a whole. We find the equivalent capacitance, the total charge, and then we analyze that from there. So that's going to be after we find the equivalent capacitance, we start with the total circuit and we can find the total charge on everything. And then we know the total voltage and we know the total charge. One of those, and I'll talk about the situations, is going to map onto one of the individual combinations. So then we're going to start with the second to last steps. We kind of work backwards through the circuit with the most simplified to the least simplified. And you'll see examples of what that means. And then you continue through this windy path through this table. And the end result of what this would look like once we work through it, again, here's a worked example that we have access to. I'm going to work through a separate example than this one. You can see that we're going to create this table that has all of the capacitances of every capacitor along with the voltage, not just of the entire circuit, but the voltage drop across each individual capacitor and the charge stored by each individual capacitor. So kind of the meat of the results will show up in this table that we're creating. Okay, so let's go ahead and look at one of these examples. So here's the example that we're going to work through. We have 4 capacitors arranged in the circuit as shown, and the first step is to identify the type of combinations of capacitors in order to find the equivalent capacitance of this circuit. So as we saw in previous videos with the rules of series and parallel, we can kind of navigate this step. So we can see that this circuit here has C1 that is in series with C2. So that dash sometimes is used to simplify it and say that those are in series. And that C4 is in series with C3, right? So we have a series and a series, and those two combinations are in parallel with each other. So I would write this as C1 is in series with C2, and that whole thing is in parallel with C3 in series with C4. So now I'm going to identify some individual capacitances from this. I'm going to have this one, which is C12, and that's going to be in parallel with C34. I actually want to keep track. I don't want to do this in one big math step because in what we're about to do to analyze individual parts, I want to know the value of each of these individual steps. So what I can say here is that C12, because it's a series step, we have C12, we can use that and find the value of C12. So 1 over C12 is going to be equal to 1 over C1 plus 1 over C2, and that just comes from our rules from our previous information on this module on how to combine things in series. And so we end up using these values as 1 over 3, and I'm going to just assume these are all the nanofarads. I'm going to keep nanofarads, I'm going to drop the units here, plus 1 over 6. So 1 over 3 plus 1 over 6, I end up with 4 over 12 plus 2 over 12. That ends up being 6 over 12. And so again, I have to invert that. So C12 equals 12/6, which is going to be equal to 2 nanofarads. I am going to box that because again, those intermediate results are numbers that I'm going to want to keep. I can then solve for C34 in the same way. 1 over C34 is going to be equal to 1 over C3, which is 1 over 5, plus 1 over 4, which is 1 over 20. And again, just doing my fractions here, I get 4 over 20 plus 1 over 20 is equal to 5 over 20. And again, I have to invert that. So I get C34 equals 4 nanofarads. So I have these two intermediate steps. And so what that means is I can basically draw this circuit, which looks like C12 on top. And then that is simply in parallel with C34 on the bottom. And those are in parallel with each other and with the voltage of the battery. And so from that combination, I can then say that the C equivalent, which is essentially C1, 2, 3, 4, right, using all of them, is going to be equal to the C12 plus C34 because it's a parallel combination. So C12 plus C34, and that's going to be because it's a parallel combination. The previous inverse rule was for series combination. And so then we end up here getting my equivalent capacitance of 6 nanofarads for my CEQ is 6 nanofarads. Okay, so I've completed step one, which is simply to find an equivalent capacitance. And so now what I want to do is I want to start building out my table by looking at the entire circuit. So I'm going to come down here. I'm going to say, okay, step two is going to be to look at the entire circuit. So the total circuit, which means that I'm going to use this result, right? We have this equation for capacitance, which is charge per volt, right? And so what that allows me to do is say that, okay, my total charge in the circuit is going to be equal to my total capacitance, which is what we call the equivalent capacitance, times my total voltage, which is the voltage of the battery or the voltage of the power source. And so from this, right, if we remember that the voltage of the battery in this problem was 12 volts, I can see here that Q total is going to be equal to 6 nanofarads, that previous result we had, and then times the given 12 volts that we had from the statement of the problem. And so we can see here that this is simply going to be equal to 72. The units of that are going to be in nanocoulombs because it's nanofarads times volts. So I get nanofarads for my Q total. So I've now kind of decided on like what's happening with the whole circuit. And now I'm ready to make the table. So at this point, I'm going to go ahead and make my table. And I'm going to do this here. So I'll make my table. And the table is going to have the values of the capacitors. And we're going to start with the equivalent, the total, which again is the equivalent capacitance. So we're going to put the total circuit at the top. So this is going to be the total circuit. The CEQ for that, if we remember, was going to be equal to 6. I'm going to put the calculated values in here. So that's going to be 6 nanofarads. And I'm actually just going to keep the units up top to keep these columns nice and easy. And so that's 6. And then I'm going to put in the charge on each one. So remember we have this equation that C is equal to Q over V. So Q is equal to C times V. And so for that reason, what I'm actually going to do is I'm going to put the second one as voltage. It doesn't matter, but I like to have it so that I have that the last column equals the first two multiplied together. And so we can then say that this volts is going to just be in volts. And the volts for the total circuit was equal to 12. That was given in the problem. And then I'm going to have my Q. And that Q is going to be in nanocoulombs. And we just found the Q total, which was going to be this 72. So we have the total circuit at the top. And now I'm going to go ahead and just list all of the individual capacitors. Now this might seem a little tedious at first, but it works out really nicely. It's a very organized way that you're not going to make careless mistakes if you can kind of keep track of everything in one clear way. And so I'm going to put all of my individual capacitors. So these are my individual capacitors. And then I'm going to put all of my individual intermediate steps. So remember I had a C12 and I had a C34. So these were going to be my intermediate steps. And at this point, I'm actually going to just fill in all of these values for what I was given. So these were all values that we had found previously. I'm going to put a star here for which ones were found in steps 1 and 2, right? And so now let's go ahead and see. So this is the making the table. And why did we make this table? Well, the key idea here is that one of these two values is going to map onto one of the intermediate steps. So one of these two values will map onto an intermediate step or more. So in order to decide which one, this is where the thought process comes in. We have to look at where the circuit came from and decide if we're looking at a series or a parallel situation. So to figure out which one, look at the last step and see if whether it is series or parallel. The last step in this scenario for finding the equivalent capacitance is this one. And we can see that C12 is in parallel with C34. So I'm going to redraw that down here just for clarity. So I'll say over here that we have the last step was going to be C12 was in parallel with C34 and the battery. So remember that because it's in parallel, that means that the delta V is the same, right? We can imagine that the delta V of the battery, all of these lines are all at the same potential on the left-hand side, and all of the lines on the right are at the same potential as the left-hand side, as the right-hand side of the battery. And so all of those have the same potential. And so I have this very important result, which is that delta V of the battery is going to be equal to delta V12, which is equal to delta V34. So in this case, it's actually going to be the voltage that maps. So this is going to be delta V is the same, so it's the voltage that maps. And I'm going to put in the word total here, so it's the total voltage that does this so-called mapping. They don't have the same charge in these parallel paths. If this had been a series path, I would be like, oh, they're in series with each other. They're going to have the same total charge. And the previous example I had put up that is worked out is an example of that path. So we're going to then map here. We're going to take this and we're going to map the 12 volts onto the C12 and the C34. So the 12 volts gets mapped onto those steps. That's the key thought process here. And now we have just started a little windy path logic puzzle through this table. So what we can do now is we can calculate a value, because we know here that Q equals C times V. And so if I have Q12 is equal to its capacitance times C times its voltage, that means that this is going to simply be 24. So I just actually calculate that. Here I'd have 4 times 12, so I get 48. So you just calculate these. Once you calculate a value in an intermediate step, so once you calculate a value for an intermediate step down in these bottom rows, that means that that value that you calculated maps onto something else. So now you think about what created that C12, right? So the C12, if we look here, we have that C1 was in series with C2, right? So that means that they have the same charge, which means that C12, the Q, the charge on 1, 2 as a combo is equal to the charge on 1, which is equal to the charge on 2. And so we have this other mapping step, and I'm going to mark this one in purple, right? So this is going to be another mapping step. I can then take this Q12, this is my Q12 because it's for C12, and it's going to map onto C1 and C2. So that's a 24 here. And then likewise, the 48 is C34. C3 was in series with C4. So that tells me that Q34, which was 48, is going to be equal to Q3, which equals Q4. So it is like a logic puzzle. We come through and we end up with 48 and 48. At this point, we know 2 of the 3 values in a column, and so we can then calculate the third value. Sorry, 2 of the 3 values in a row, so we can then calculate the third value. And so we know here that V is going to be equal to Q over C, and so we can just do 12 divided by 3, so that's going to give us 8. And so then that's going to give us 24 divided by 6, that gives us 4. And then here we just get 48 fifths. I'm just going to leave that unsimplified, and 48 twentieths. And we now have literally every voltage drop and every charge on every individual capacitor calculated. Again, it's like a windy little logic puzzle. If it's series, then the charge maps. If it's parallel, then it's the voltage that maps. And we go through the whole circuit that way. So here's the initial list of steps, as well as another example that I'm just showing again. And you can see here that the last step was going to be a series step versus the parallel step that we just did. And so since the last simplification of finding CEQ here resulted in a series step, then at the end, at the table stage, we can actually see that it was the total charge on the capacitor which mapped to one of the intermediate values. And so then that is an example of how you'll choose the total charge to start the windy path through the table, versus when your last step is a parallel step, that's when you choose the voltage to start. And here's the full kind of worked example for that one as well. So I hope that this video helps you understand the really methodical and logical way which you analyze these circuits that have multiple capacitors.